This representation is MLP. Actually, you can replace it with any CNN. Anyway, for the encoder here, then the output will be the mu and the sigma, okay, for feature K, such as the degree of smile, the gender, the beard, okay, it will give you the mean and standard deviation, okay? And after that, we will combine into, we can estimate the latent variable, which is given, well, actually I can put Ki to be okay, here. The mean and the standard deviation for some feature K. Again, the total number of features must be specified by the user. Okay, it's given by the user. You need to determine you want how many features. And then the encoder of VAE will run the mean and standard deviation automatically. Once you output the mean and standard deviation, we can estimate, okay, or we can calculate the latent variable with this equation here. That's what I'm saying. Each time, even you have the same input X, you may get a little bit slight difference of the output. That's because this is generated randomly from a standard Gaussian distribution. That's the reason you won't get a fix, okay? It doesn't give a fix latent variable or feature vector like CAE. Okay, then once you have this one, then we can input it to the decoder. Okay, so for this one, we try to estimate just like what we did here. Okay, we want to try to, given input X, what should be the distribution? See, and hopefully, okay, we look for the Z that will follow a Gaussian distribution. Okay, not a standard Gaussian distribution, but a Gaussian distribution given by Z here. And then for the decoder, for a given the latent variable, we try to find what should be the maximum likelihood that you can observe the output X, which is, it should be exactly the same as the input. So that's it, okay? That's the purpose of VAE here. Okay, so this is run. We run this, okay? A K is the feature, case feature. You need a total of K, okay? So for this one, you can specify as a Z1, Z2, and up to K. Okay, it's something like this, okay? So the Z here will be something like this. Degrees of smile, okay? The distribution for the smile, or distribution for the skin tones, gender, beard, glasses, and so on, okay? That's what we do here, okay? But for the user, this is user specified. Okay, parameter. You need to determine what should be the size of the features, okay? But this is nothing but another neural network, okay? This is also another neural network. Okay, that's it. Now, I won't go through all the details, but let's take a look. Let's take a look how it works. Okay. Let me see how to set it. Okay. Let's take a look for this model here first. Okay, for the encoder, we will train the encoder network, no matter it's MLP or CNN. Okay, we need to estimate the probability of Q, but we run a neural network, okay, which we use a big Q to represent the neural network you are going to run. Okay, that will follow the required distribution. We put a Y here, which means what? The parameter of the encoder you are going to run. Okay, and P of Z here we assume that it will follow the standard normal distribution. Okay, it will follow the standard normal distribution. Okay, I put an I here means is identity. If k equal to 3, then actually it can be a covariance matrix, but we simply assume it's a diagonal matrix. So we estimate the standard deviation for each one. We don't find the covariance between the feature 1 and feature 2, and feature 2 and feature 3. No, it's too complicated. Okay, we simply just use diagonal. Okay, so that's why. Then it is supposed. Then this one, I mean, this should be Z. Okay, the variance, the total variance should be. But identity matrix is nothing but for a 3 by 3 is what we expected. Okay, this is what we expected. Okay, a standard Gaussian distribution. Okay, and then what we try to maximize is what? Given Z. Okay, given Z, then you will find the maximum likelihood that you can observe X. Okay, that's what it's trying to do for VAE. Okay, but remember, no matter it's encoder, decoder, they are nothing but the neural network. Okay, neural network. Okay, so for this case here, Q of Z, we would like the Q of Z or the output mu k sigma k, and then we calculate the latent variable is given by this equation, so that Q of k also will follow a Gaussian distribution. It's follow a Gaussian distribution, okay, with the standard with the mean, okay, mu q, and the covariance, okay, the diagonal covariance like this. That's why we try to run, okay, and Z, I already mentioned that, okay, and then Z will follow this Gaussian distribution, okay? That's what we are looking for, okay? That's what, okay? Everyone follow me so far, okay? That's good, right? Good, okay? Now, the last question here is how to set up the loss function, okay? How to set up. For the CAE, it's quite easy, okay? We just try to minimize the reconstruction error. That'll be good enough, okay? But for VAE, to make sure the Gaussian function, okay, the encoder will follow the Gaussian distribution, given P of Z is a standard, okay, Gaussian function that we need to do something about it, okay? So the difference is we'll put some restriction for the distribution of Z, okay? so that is it right? Is it right? Okay. That's why we try to run. Okay, so for different images, for different degree of smile, then you will have different distribution. Okay, that we put the restriction for that. Okay, so for the implementation, for the encoder, you will run, I already mentioned this, the mean. This is the mean vector, okay? Mean vector for all the features. And diagonal covariance, okay? Then for the decoder, now we sample the latent variable from the standard Gaussian distribution, as I mentioned right here. Then we create a random variant, okay? That's so-called random. That's because we use a random variable here, okay? That will follow standard deviation, so that the latent vector, okay, or the latent variable will follow a Gaussian distribution with the mean vector mu and the diagonal variance, okay, sigma here. Okay, and if you want to learn more about how to do the backward propagation, then the gradient can be learned from here, from this two values. Okay, that's the idea. That's the trick. Okay, it's to run from the mean vector and the covariance matrix. Okay, then the reconstruction is trying to find the decoder. Okay, that will well reconstruct X. Okay, so that's it. So the objective. Now the idea is here. This is we try to estimate. I got another picture. Should be somewhere. Let me see if I can. Right here. Okay, right here. Okay. Now this the blue distribution here is what? That's a conditional given X. I want to know what should be the probability of the latent variable Z. It is very difficult to measure because you need to try out or it's not possible to train for every possible input X. Now, so we simply assume what? The Z will follow a well-controlled distribution. That's the idea. Everyone follow me? I mean, the blue distribution here could be the actual, okay, or the observed distribution, or the actual, but it's not manageable. So instead, we simply give a standard or much better, well-manageable distribution. Usually, we simply take it as what? The Gaussian distribution. That's it. To approximate, okay, to approximate the actual idea. Okay, so that's the idea. Okay, so what mathematically what you try to do. Okay, I won't talk about all the details, but let you know something. Okay, so here is the objective. Okay. We want to. This is the actual distribution. Okay, given X, what should be the distribution? But Q is you make some assumption about the observed, okay, distribution given X. And P distribution is the actual one, which you may not know it. Okay, you know what I'm saying? And this is the KL divergence. You know what KL divergence is, right? If we put KL, F, G, it means what? F times log F divided by G, right? Everyone follow me? Okay, this is a KL divergence. But if we take it discrete, and we take the summation here, okay? We take the summation here. Okay, so F could be the ground truth, G, or F could be the observed, and G will be the ground truth, okay? Or vice versa, okay? So that's it. This is our objective. We try to estimate the probability from the neural network will be truly represent the unknown distribution. Okay, anyway, here comes a mathematical, I will skip that, but I let you see how you can take a look, because it needs a lot of mathematics. Here anyway, that's the objective, okay? I already mentioned that, okay? And I say it can be shown, this is equal to this one, okay? That's by this, okay, I already said it, okay, Carroll divergence here. If you want, you just can go through the details, okay? Go through the details, starting from here, from the Carroll divergence here. And finally, we can see it becomes this term, okay? Becomes this term, this is our original, okay, objective function that is equivalent to this one. It's maxima, because as I mentioned in deep learning, the objective is given by loss function. So we need to convert the maxima to minima. So we will put minus sign here, okay, minus and plus Carroll. But anyway, let's take a look of the very first term. Okay, the very first term, E means expectation, 期望值, E 是期望值, mean the mean, the expectation, okay? Expectation that what? That will maximize, that's based on maxima likelihood, okay? This, we try to maximize the maxima likelihood. Given Z, then the output will be X. So remember, the very first term is nothing but the reconstruction error. The very first term here, because what? Given Z, we try to make the output X to be maximum. Just like what you input, okay? What you input to your VAE model, okay? So the very first term here is nothing, okay? It's nothing but the reconstruction error, but it's based on maximum likelihood. When you read the programming code, you won't see this because the maximum likelihood is much more difficult to solve for the problem. So usually this is simply replaced with this. It just use mean square error or cross entropy. Okay. Instead, it won't use maximum likelihood because it is quite difficult to solve. You know what I say, maximum likelihood, right? For given X, you need to try out what all the possible Z, okay? Then you can obtain the X. That will be very difficult. As we mentioned here, see that? This original, you can observe X, you need to try out every possible Z. No, it is not possible, right? To implement, okay? So instead of for programming implementation, this is given, okay? This is given by the maximum likelihood. Or for the loss function, we try to minimize the reconstruction error. You can go for mean square error, but the only term difference compared to the CAE is this right here. This right here. It means what? You try to minimize the KL divergence between what? P of Z given X. What should be the distribution of Z? Okay? Everyone follow me? It's set up the constraint. Like any optimized model algorithm. This is our objective. We try to minimize the difference between the input and output, but under the constraint that the Z, the latent variable, the learned latent variable must be as close to the probability of Z. And since we know nothing about Z, we simply assume P of Z will follow a Gaussian distribution. That is the idea. Everyone know what I'm saying, right? This is the result. So you can think of this loss function as a regularized reconstruction error. It still try to minimize the reconstruction error under the constraint. It's so-called the regularization. 好，第二个 term 是叫做 regularization. It used a lot in deep learning. It try to regularize or set up the constraint so that the Z must be, the estimate Z must be follow the Gaussian distribution. And this term here is the same as I just show you. Whoops. Where did I show this? No. Go upward. Whoops, where? Right here. Okay, that's it. That's the idea. Okay, that's it. This is the regularization term, right? See that? We try to make our estimate given X, or should be the Z, that will follow the manageable distribution Z. Okay, and Z will be Gaussian distribution. That's the idea. Okay, just for the regularization. Okay, so let's go back to our objective. Here is our final objective. It's right here. Okay, so we add an additional term based on the mathematical equation. Sometimes people will put a coefficient here. Okay. But in the mathematical equation, actually, we don't need any coefficient. But some people might put the coefficient to emphasize you want to concentrate more on the reconstruction error or the estimate the latent variable. But it is not required. But if you see something called, if I'm correct, called beta VAE. That is, if put a beta here, then this beta is user specified. 你说你可以自己放，你要强调呢，重建误差小一点，还是呢，你要让你猜的 ，given 看到 x， 你要猜的这个 latent variable 呢，更接近那个常态分布，你可以用 beta 去调控。But in the original mathematical equation, there's no need for this regularization coefficient. Okay? But anyway, somebody used it and called it beta VAE. That's it. That's the only. So if you want, you can try it out. Okay? So that's it. Now, the next problem is how to solve for this scale. Okay? So it's easy. Okay? Because we assume the Q, right? Because Q is so for the encoder. So we simply try to learn, we make this neural network encoder to learn the mu and standard deviation. So it will follow a Gaussian distribution. And P of Z is nothing but a standard Gaussian distribution. Okay? So that's it. Okay? So with this, both are Gaussian distribution. For implementation, here I will show you for the implementation. Put it where I put it. For the implementation, the finally term will be okay. So here, okay. This is a KL divergence term here because you will both are follow Gaussian distribution, right? Then we can write the Carroll term like this. This is the trace, okay? This is the trace of the matrix, of the covariance matrix. The trace is nothing but we just add up the diagonal element, okay? The trace, okay? And mu is okay, for the input x. K, remember, K is the dimension of your latent variable here. K is here. K is the latent variable, okay? K is the latent variable here, okay? Then we calculate determine, okay? The determine of the covariance matrix, and we take log. Now, it can be further simplified. A little bit trivial, but this is the final form. So when you read the Carroll's code, the regularization term, you will see this term here. Okay, this is the final term you use. So the very first term is based on the mean square error. We try to minimize the reconstruction error. The second term, we try to make the latent variable now will follow Gaussian distribution, and the second term is simply given by this one. Okay, sigma k is right here, the sigma k, and mu k. Here, k is the case feature. Okay, so you should put this, the lowercase k should be equal to 1 up to the uppercase k. Okay, k equal to 1, should be k equal to 1. Okay, so when you read the code, what you see is this equation. Okay, it's this equation. It's much easier to implement. Okay, so that's the VAE. All others, the model can be is nothing but just MLP or CNN or transformer. Okay, so that's it. Okay, so it might get lost. Okay, but just try to figure this, what I put here, just what I put here for, okay. This is our original, okay, objective function. Then we can convert it into the maxima, okay. Maximum likelihood for the reconstruction error, okay, or the reconstruction x, output x. And also we try to minimize the Carroll divergence between the estimate latent variable and the Gaussian distribution Z, okay. We just make the assumption, okay. And then this is how we get the final loss function. Okay, and Carroll can be replaced with this equation. Okay, right here. Okay, that's why you when you read the code, that's what you got. Okay, that's what you got here. Okay, so that's it. Okay. A little bit complicated, but the implementation. The only thing you need to remember is this architecture here, especially right here. That's what you learn, okay? The difference with respect to CAE. Okay, that's what you learn here. You will learn the mean and the standard deviation. And the latent variable, it's given, it's randomly sampled from the standard normal distribution. So every time you won't get exactly the same image. Okay, that you must keep in mind. But it can generate a wild diversity of the input data, okay, compared to the CAE. Okay, that's the good thing about VAE. Okay, so that's it. And also I show you a lot of examples here about how to build the autoencoder and CAE and VAE in Keras. Okay. you can go through the details. Okay, I showed the code. Okay, downloaded from the websites, and also I show you some of the code. Okay, presented by my previous graduate student for. Okay, I can skip some of it. Okay. You can use for image denoise. Okay. That's what I'm saying. For image denoise, to train CAE, the input must be a noise image. You must add noise. For defect detection, why you are not supposed to use CAE? For defect detection, if we can train only normal sample, okay? Because we don't have too many defect sample, and you might see a wide variety of the defect. So the easy way to use the autoencoder by training only normal sample. But if you go for CAE for denoise application, what you should do? You need to provide a defect, and also the output. If this is, then you need to provide the normal version of the input so that you can identify the defect here by subtracting these two difference. Okay, you know what I'm saying? And then hopefully we can retain only the defect. But you know, this is almost impossible. Why is almost impossible? Because you need to prepare the pair of defect and its corresponding normal sample. So it would be better to go for the VAE. If you go for VAE, now if you go for the VAE, we train only normal sample. We train only normal sample. Okay? And then for the trend, okay? For the trend VAE. Now if we input, okay, after the training, because we train only normal sample, if we input a defect sample here, then it will convert this defect image into what? Because we train only normal sample, it will convert it into a normal pattern. So in this case, we can simply subtract the difference and hope usually you can preserve the defect. With this approach, you don't need a pair. You don't need to prepare a defect image and its normal version. It is very difficult to do it. Okay, you know what I'm saying? That's something VAE can do. Okay, something VAE can do. Okay, but I didn't say VAE is always better than CAE. No, I didn't say that. Okay, but that's one of the applications. Just like the example here. To use CAE for denoise, you need to prepare the noise image, and hopefully you can do denoise but you need to prepare the pair for the training. Okay, it's too tedious. Okay, too tedious. Okay, then for the VAE, show a lot of Keras code here. Okay. This one saying this KL loss. See that? The KL loss. Did you follow what I'm saying here? Okay. You can just go back to look for the equation. Okay. The scale loss. And for the reconstruction loss, it use a binary cross entropy. Okay. The example here, it does not use the mean square error. Okay. Okay, so that's some details. And this example show you if I change Z1, Z2, what can you do? Okay, you can rotate, right? The handwritten digit, see that? See that? By changing the Latin variable, okay, you will some will represent the orientation, okay? And some will represent the digit, see that? Okay, the shape, right? The shape. And some will represent the orientation. Okay, you will rotate from left to right and change from 7 to 9 or to 0 or something. Okay, that's what we can do with the Latin variable. Okay, which cannot be done with CAE. Okay. Okay, and this shows you some of the application. That's what I'm saying. If you go for the CAE, see that? You need to prepare the defect and its corresponding defect-free version for the training, which it may not be possible. See that? It's very tedious. 这个太辛苦了，你自己要去收集坏的，收集坏的还不够，你还收集它好的，而且是它对应的那一个。When I say the corresponding defect-free they must be present exactly the same background, which is almost not possible to do it, okay, in reality, okay? So the better way to go is go for the VAE, okay? Here, just show you the example of the model for CAE, okay? Okay, and show you more details about each layers. Okay, and the code, okay. Okay, and also you can go for here, okay. Then you can go for the VAE, okay. The VAE, the training is simple, just to train the normal sample. Okay, you just train the normal sample. But if you input the defect, here, it may not show. But anyway, here's the code. Okay, here's the code. Okay, you can remove the defect, and by subtraction, the input and output, then you can find where the defect is. Okay. That's the idea about VAE. Okay, that's what you can do. You can do all the details code. Okay, for that. Okay. So how much time we have here? We have 5 more minutes. Okay. So after the training, that's what I'm saying. If you input a defect test image, then the trained VAE will remove the defect here. Okay. That's what I'm saying. You can remove. So it's much easier. Just by training only the defect-free samples. Okay. The last thing I would like to say is about. I didn't say anything about decoder. Remember, I said the decoder you need to do deconvolution and upsampling, right? Because desampling you will reduce the size, right? Most of the time reduced by a factor of 2, okay, by a factor of 2. But for the decoder, it must increase or upsampling also by a factor of 2, okay, 2 times. Now, the most easy way, the upsampling can go by interpolation based on nearest neighbor interpolation, or by linear interpolation, or by Q, okay, interpolation, 可以用内插 because we are doing upsample, right? So you need to interpolation, okay? This is something you can do, that's provided by Carol, okay? Here you have a lot of choice. You can, this is given by Carol, okay? This parameter you can choose based on aerial, by cubic, by linear, by Gaussian, by a lot of, okay. Now let's take a look, the nearest neighbor interpolation uppulling. Suppose we do down pulling right here, then in the decoder, the corresponding layer, suppose the input is upsize 2 by 2, I want to upsample it to be 4 by 4. So what can you do? Because the input is 1, 2, 3, 4. Now, this 2 by 2 becomes 4 by 4. Here's what you can do. You just insert 1. This so-called nearest neighbor. Every neighbor will have the same value 1. And this will have the same value 2, and 3, and 4, and so on. What will be the result? If you apply this rule, you will see the mosaic effect. 这个马赛克效果，知道？是被打马赛克 right? It's a mosaic effect. It's not a good approach, but it's easy, right? It involves no calculation, no nothing. Okay. The other way, a little bit odd, but he used, okay, in the early version called maximum pooling. Here, this is in the process in the encoder. Okay, this is the process in encoder. Suppose this is the we have the feature map like this. It's 4 by 4. Now we are going in the encoder. It will be reduced to be 2 by 2 by max pooling, which means I reserve, okay, because the pooling size is 2 by 2 with strike up 2. So the maximum pooling you will preserve 5 here, but at the same time you must recall where is the location of this maximum value. You must memorize the location. Okay, I didn't say you, I mean the code will have to. Now, then we have a 6. You will record the 6 here, and 7 here, and 8 here. Now, the corresponding decoder, when the input will be upscaled from 2 by 2 to 4 by 4, this is what you can get here. 1. Why you put 1 here? Because 1 is from this location. So we put 1 here. All the neighbors will have the value of 0. Then why 2? Why we put 2 here? That's because this is come from this upper left corner. Everyone follow me? Okay. Now, you might wonder, you have so many zeros. It doesn't matter after the convolution, right? After the convolution, if we go for a 3 by 3 convolution, then the 0 value will be gone. Okay, will be gone. Okay, that's the idea. That's based on the maximum pooling. Okay, so but for this application, you need to memorize where is local maximum value, and when you come to the decoder, you need to bring back the location and fill the current input value. Okay, that's the idea. Okay, but most of the time, you can go for let me oops. Yeah, here's if the signal is one dimensional, this is 1D nearest neighbor. We just okay, the neighbor. Okay, the blue one is the neighbor. Okay, we just this is the linear, right? Interpolation. And if we go for a cube, okay, a cube function, then it's much better. For two-dimensional, okay, because image is two-dimensional, so you need to fill the linear, okay, based on this 4 data point. Based this 4 data point, then we find the linear interpolation. But if we go for the nonlinear by cube, okay, so again, also we use this 2 cubic line and we interpolate the corresponding point, okay, much more. But anyway, you can simply just select it from the code, okay. But actually, Keras provide the so-called transpose convolution, because no matter you go for the nearest neighbor or maximum outputting, there's no parameter that can be determined automatically, okay, by your loss function. 你说你只要用这个方式，所有的值呢都已经是定住了，你没有办法改。Not like the convolution. You can design the filter, right? So, for the transpose, okay, for the convolution in the decoder, you can use transpose convolution. Let me just give you an example, okay? Then we can dismiss the class, okay? If you are interested, you can take a look. There's a lot of transpose convolution, but let me just show you this example here, okay? Now, suppose we have the input. This is the input, okay, feature map, which is 3 by 3. S1, S2, S3 are the element value. Now, and we have a kernel or filter also upsize 3 by 3. Okay. Now we want to upscale the feature map from 3 by 3 to 6 by 6. Okay. 6 by 6. So here's what you can do. Now 3 by 3, you want to upscale to 6 by 6. So we just insert 0 in between. See that? See that? 第一个先内插0，看到没有 ？3 by 3, we insert, okay, column by column, okay, and row by row, so that the original size 3 by 3 will become 6 by 6. And then we put the kernel. Now we are going to run the kernel, okay? All the elements, they are the parameter run by your convolutional neural network, okay? So first we put the kernel right here, okay? Put A5, the center should be right here, right? Right? A5 should be here. So we made the convolution. So A1 times what? That's what can you get here? What can you get here? Will be X1, okay? We put A5 here, then we calculate, okay, all this value, okay? Everyone follow me, okay? So that's what you got, all the value, okay? What you got, all the value right here, okay? First we put, I put the center, I should say, I put the center right here, starting from here, okay? Starting from here. A5, put A5 here, okay? Outside the region, suppose they all have the value of 0. So when you do the convolution, that will be A5 times X1. And all the remaining value will be 0, right? 0, including the boundary. So Y1 will have the value X1 times A5, okay? So that you can check for Y2, okay? When you move, okay, A5 right here, okay, A5 right here. What you got is what? A4, okay, times X1, okay? A4 times X1 and what? A6 times X2. That's what you got here. So after the convolution, so that's how it runs the kernel elements, okay? That's so-called transpose convolution. This function is given by Keras, okay? So the transpose can be 2D or 1D, okay, for time series. So you can do so it means you don't need to use upscaling. You can simply use convolution to learn the the filter, okay, so that hopefully the reconstruction image can be better, okay, not just like what I just mentioned. You may not just go for the maximum pooling, or especially for the nearest neighbor, right? The final result, you will get a mosaic effect. So the detail will be lost. You can only get some a black image, okay, in the final output. Okay, so convolution could be better. Okay, so I'm not finished with autoencoder yet. Okay, next week I will say something about diffusion. Okay, and mask autoencoder. Okay, and mask also which are the two up-to-date autoencoder model for image generation. Okay, so then we can finish it. After that, then we can go for semantic segmentation or object detection. Okay, so that's it. Okay, that's so much for today. And you need to work on your term project, okay, as soon as possible. Don't wait for me. Okay, just based on my recommendation or comments on your outline. Okay, just go for it. Okay, okay, that's it. Then see you next week.